Me. I would like to, so the second speaker of today is David Mateos from Santa Barbara, and he will talk about RHIC physics and string theory, the fundamental story.
Thank you very much to the organizers for the opportunity to speak here. Also, thanks to my collaborators in recent years who've made a lot of this work possible. And most importantly, thank you to Hiroshi for lending me his pointer. So, the plan is to give you some motivation, then I'll discuss phase transitions for fundamental matter. The word fundamental in the title doesn't mean what I'm going to tell you is very important. It means it refers to the behavior of fundamental degrees of freedom. Then I'll discuss viscosity issues, photon production, finite density, and then I'll leave with some future prospects. So let me remind you that after 34 years since the discovery of asymptotic freedom, QCD is still a challenge. We have no truly systematic methods to analyze it. The lattice is good for some observables, but not for others, especially dynamical ones. And so it's been a long-standing hope that if you reformulate QCD as a string theory, that might be a helpful thing to do in order to address some non-perturbative aspects. And by now we have a lot of gauge gravity examples. But unfortunately, because of its asymptotic freedom, QCD is not accessible, the dual of QCD is not accessible via supergravity exclusively. So this means that if you're interested in certain quantitative aspects of QCD, say for example, what is the mass spectrum at zero temperature, then presumably you have to go beyond supergravity. You have to do string theory. However, this does not mean that certain predictions from supergravity may not be universal enough to apply to QCD, at least in certain regimes. And understanding what predictions and what regimes is actually part of the challenge. And so, one of my favorite examples of that is the computation of the ratio between the shear viscosity and the entropy density of some strongly coupled plasma. This turns out to be the same for all non-abelian plasmas for which we have a gravity dual. There's absolutely no counterexample to this in the large N limit and large coupling limit. This holds for plasmas in different dimensions with different matter contents, with or without a chemical potential, etc. And so this makes one suspect that if QCD, the quark gluon plasma of QCD, just above the confinement is really strongly coupled, then perhaps since this seems to be a property shared by all non-abelian plasmas at strong coupling, perhaps the viscosity over the entropy should come close to 1/4 pi. How do we check that? Well, we don't know how to calculate it from first principles, but we can go to RHIC, where you collide heavy ions, and you can do simulations and then try to see what the results suggest, and they do suggest that the ratio is very close to 1/4 pi. And if you ask me later, we can discuss how close to 1/4 pi. And so let me make a few observations about this. The first one is that when this eta and s were calculated, the authors who did that did not know this ratio was going to be universal. And so not knowing should not discourage us from calculating. This was observed, the universality was observed later. The second point is that the reason why this is universal is because it is related to a universal property of the gauge gravity correspondence, namely the fact that the gravity dual of a deconfined plasma always contains a black hole horizon in it. And both of these quantities are related to properties of black hole horizon. And so what I'm going to tell you about today is what happens when you combine the previous observation with another one, which is the fact that if you want to add fundamental degrees of freedom in the fundamental representation, in ADS-CFT, one way to do that when the number of flavors is much more than the number of colors is to add D-brane probes in this previous background. The reason for that is that the closed strings, as you know, are typically dual to gluable states or states constructed out of gluons or adjoint fields. And in the same way, the open strings you introduce by introducing D-branes are dual to bound states of fundamental fields, such as quark-antiquark bound states. Now, most of what I'm going to say is universal for a large number of models of this type, but I'm going to concentrate, just for concreteness, on D7 brane probes in the background of D3 branes. But bear in mind that what I'm going to say applies much more generally. I'm just telling you the universal features. Having said that, I want to emphasize again that none of these models is QCD, and so you should interpret everything I say with caution. Okay, so let's discuss phase transitions. As soon as you start thinking about embedding D-brane probes in the background of a black hole, you realize there is going to be a phase transition. The reason for that is that the size of the black hole is proportional to the temperature in the gauge theory, whereas the distance between, the asymptotic distance between the branes and the horizon is proportional to the quark mass. And so if the quark mass is much bigger than the temperature, then of course the branes will deform a little bit because of the gravitational pull from the black hole, but they will stay outside the black hole. On the other hand, if you keep increasing the temperature, eventually the branes will prefer to fall through the black hole. It turns out in between there is a critical embedding in which the branes just touched the horizon, and this might actually make you suspect that the transition is going to be smooth. But in fact that's not the case. If you use thermodynamics, you realize that the free energy is minimized over here, and as you increase the temperature, suddenly it jumps over here and it's minimized by one of these embeddings, so this one is skipped over. And I want to emphasize that this transition is not a confinement-deconfinement transition. The theory is in a deconfined phase here and here because there is a black hole in the background. Okay, so there's no area law for the Wilson loop, the entropy density scales like n squared, etc., etc. This is a phase transition associated to the behavior of the fundamental degrees of freedom. And so how do we distinguish these two phases? Well, the most significant difference is in the spectrum. So if you look at the spectrum of mesons in this phase, it's very easy to see that it's a discrete spectrum with a mass gap given here, which scales like the quark mass over root lambda, where lambda is the tooth coupling, so these are very deeply bound mesons. And this scale also sets the transition temperature. Now, we also have free quarks over here, which are massive. These are just strings stretching from the tip of the branes down to the horizon. And the point I'd like to emphasize is that both these sets of degrees of freedom are absolutely stable in the large n, large tooth coupling limit. And so the interpretation of these mesons is that they survive if the quark mass is sufficiently large, then these quark-antiquark bound states survive deconfinement. The theory is in a deconfined phase already, and nevertheless you still have a discrete set of bound states. On the other hand, on this side, there are actually no quasi-particle-like excitations. This is very important, and I will actually convince you, hopefully, of this by computing a spectral function, and you'll see there are no resonances or peaks that you can interpret as quasi-particle-like excitations. And so, going back to this statement that the heavy mesons survive deconfinement, this prediction is in perfect qualitative agreement and good semi-quantitative agreement with the lattice prediction. On the lattice, people compute spectral functions and they see that some peaks survive. For example, for the Jape side, they give you a temperature of dissociation in between 317 and 403 MeVs, which is above the deconfinement temperature, which is around 175 MeVs. And you can compare that to the gravity prediction, which is written down here. And you notice that the lower bound is exactly the same as in the lattice if you exchange the 7 and the 1. So now that you're all convinced, let me tell you about the viscosity of fundamental matter. So, as you probably are aware, there is a conjecture by these authors that eta over S is bounded from below by 1/4 pi for all relativistic plasmas. As far as we know, this bound is exactly saturated by all theories for which we have a holographic dual at large n and large lambda. Results from RHIC are very close to 1/4 pi. And so it's interesting to ask what happens to this bound. Is it still exactly saturated? Is it violated? Is it not? When you include fundamental matter. Of course, the motivation is that QCD does have fundamental matter, but moreover, at large n, the effect of the quarks is the first and leading 1/n correction. So it's interesting to understand 1/n corrections to this result. How do we calculate this? That's actually really simple, because the viscosity is given in the gauge theory by this type of Kubo formula. So you can extract it as a zero frequency limit of a 2-point function of the stress energy tensor. Now this is very easy to compute using holography because the stress energy tensor couples to the metric in the bulk. And so the contribution from fundamental degrees of freedom to viscosity is basically given by this two-point function, which is in turn holographically given by the second derivative of the action of the d branes with respect to the metric. So if you do that calculation, and it's also very simple to calculate the correction to the entropy density, you find that both of them are non-trivially corrected at the leading order in NF over NC. However, the correction is such that the ratio is exactly preserved. It's still 1 over 4 pi. And so, for example, I've written down for you here the viscosity. This one gives you the leading n squared result. And this term here, where h is an order 1 function, is the correction coming from fundamental degrees of freedom, which is suppressed by NF over NC, as you would expect. But note that it is enhanced by a power of lambda. This is a strong coupling prediction. This is not something you can guess by doing large n counting. And the same is true for every transport coefficient and every thermodynamical quantity. So for example, it is true for the jet quenching parameter that the previous speaker was discussing. There will be an order lambda NF over NC contribution to that. And so it will not scale as root lambda simply, if you include fundamental degrees of freedom. The origin of this enhancement is very simple. It's just a D7 brane tension in Planck units. Okay, so let me now move to photon production. So why are we interested in photon production by a thermally equilibrated quark-gluon plasma? The reason is that photons are very, very valuable probes. The reason being that because of its finite extent and because the electromagnetic coupling constant is very weak, essentially once a photon is produced, it escapes undisturbed. And so it carries very important information about the point of emission, such as the local temperature, etc. And let me just mention that some results using ADS-CFT for massless matter have been obtained by these authors. And so I'm going to concentrate on the effect of including the quark mass. So to calculate the rate of photon production, all you have to do is compute this two-point function, this spectral density over here, which is just the imaginary part of the retarded correlator of two electromagnetic currents, as it's indicated diagrammatically here. This is just the usual statistical factor. And so we need to compute this two-point function. That's very easy because if you take, just for simplicity, NF fundamentals of equal mass and equal charge, then there's a global flavor U and F symmetry. And the overall, which is dual to the gauge symmetry on the warp volume of the D7 branes. As usual, global symmetries map to gauge symmetries. And it turns out that the conserved current associated to the overall U1, which is the baryon number, is in this case equal to the electromagnetic current. And so we need to calculate this two-point function of this object, which is dual to the overall gauge field, the overall U1 gauge field on the D7 branes. And so again, if you apply the ADS-CFT prescription, that's very simple because it's once more a second derivative, in this case with respect to the gauge field, of the action of the D7 branes when evaluated on shell. And so let me just tell you what the result is, but before that I have to make a couple of comments. The first one is that I'm going to tell you what it is, that spectral function, for this type of embeddings. The reason is that for these ones, you know already what it is. Because I told you that the spectrum over here is a discrete set of absolutely stable particles. And so the spectral function is just a sum of delta functions located at the masses, essentially, of those particles. That's the first comment. And the second one is that the results I'm going to extract here, I will not be able to compare them, the dependence on the quark mass, to perturbative QCD calculations. The reason for that is that in perturbative QCD calculations, one assumes that the thermal mass of the quarks is always much bigger than the bare quark mass. And so this one is effectively set to 0. Now, regardless of the domain of applicability of this approximation, it assumes that you have quasi-particle quark-like excitations in your plasma to which you can attribute meaningfully a thermal mass. And I'm claiming this is not the case here, and we will see that. Okay, so with those two caveats, this is a plot of the spectral function, chi, the trace of the spectral function in some units, as a function of the dimensionless energy of the photon for different values of the quark mass. This little m is just the ratio of the scale I told you about over the temperature. This one up here is for 0 quark mass, and this one down here is for the maximum value of the mass for which you have black hole embeddings. If you go beyond that, they become unstable because they want to jump to a Minkowski embedding. And so you realize there's really no structure here, no peaks that you can interpret as quasi-particle-like excitations. Nevertheless, this one over here seems to be developing some structure. And in fact, that is true, because if you go beyond, if you forget about thermodynamic stability, and you insist on calculating the spectral function for embeddings of this type that are very close to this one, remember those ones are unstable because the free energy is minimized by this one. But if you forget about that and nevertheless compute the spectral function, this is what you get. So these plots here are for black hole embeddings that are closer and closer to this one. And you see that they are developing these very well-defined, very narrow and very high peaks, indicating that as you jump to this one, you are actually going to end up with the sum of delta functions. And so quasi-particle-like excitations are appearing. Now, in order to compare with experiment using these results, you need to extract the rate of photon production from the spectral function. That's very simple. And if you do that, you get this plot. So this is a plot of the total rate of photon production per unit photon energy in some dimensionless, made dimensionless by dividing by this quantity. The deconfinement temperature here for QCD is around 175 MeVs. This is a plot for photons of 100 MeVs. And what I'm plotting over here is essentially one over the temperature. So you imagine that when your quark-gluon plasma cools down after the initial collision, the temperature drops, so you move along this axis. And the different curves here correspond to the prediction from these models for U and D quarks, S quarks, and the charm quark. And the point I'd like to emphasize, the point I'd like to emphasize is that you might have thought that because the S quark and the charm quark especially are so heavy, you might be able to completely neglect their contribution to photon production, but you see that's not the case. It's suppressed, but not hugely suppressed. And this is a universal result for all these models. The temperature at which, the temperature reached at RHIC is about twice T deconfinement, so it's over here, and the one at LHC is expected to be over here, so that's why I chose this range. And this plot over here corresponds to photons 10 times more energetic, about 1 GeV, and you see the same pattern persists. And if you go to higher and higher energies, these curves actually become closer and closer. Now, two more things you need to do to compare with experiment are take those results and plug them into a hydrodynamic simulation for the evolution of the plasma, because the temperature is not constant, neither in space nor in time, in the fireball. That's one thing you need to do. And of course, experimentally, you need to be able to distinguish between the photons that are emitted from the quark-gluon plasma, meaning the phase in which you really are in thermal equilibrium, and other sources like photons produced by the initial parton scattering or photons produced by subsequent decay after hadronization, etc., etc. And that's challenging, but presumably in the future we'll be able to do that. Good, so let me say just a couple of words about how to include now a finite baryon density. That's actually very simple again, because remember I just told you that the baryon number, this conserved quantum number, the current that's conserved associated to this symmetry is dual to the overall gauge field on the D branes. And so again, if you look at your ADS-CFT prescription, you remember that in order to turn on, to deform your Lagrangian by adding, say, the time component of this current, which is what you want to do to turn on a baryon chemical potential, what you have to do is to turn on the non-normalizable mode of the dual field, and similarly, the VEF of that time-lap component, which is just the baryon density, is given by the coefficient of the normalizable mode. And so all you have to do is repeat the previous analysis, where now you have turned on an electric field on the D7 branes. It's as simple as that. And the fall-off at infinity of this electric field is going to tell you about the chemical potential and the induced baryon density. And so, for the sake of time, I'm just going to tell you what the phase diagram looks like. It's actually very simple. What you find is that, remember I told you at 0 baryon density, as you increase the temperature, you reach a phase transition. Thank you. And what happens is that that phase transition persists all the way up to a critical point. If you go beyond that critical density, there's no phase transition anymore. And so in the last 5 minutes, let me just quickly go over some future prospects. This is just a biased list, but I think it's interesting nevertheless. So the first one is, just to recap, I hope I've convinced you that horizons encode interesting properties of quark gluon plasmas. For example, static properties of horizons, such as the area, give you the entropy density. Small perturbations, the behavior of black holes when you perturb the horizon by a small fluctuation, tell you about near equilibrium properties of the plasma, such as transport coefficients, like the viscosity, etc. And so one thing that I think is interesting to do in the future is to look at now large perturbations, because those will tell you about far from equilibrium properties, such as collective instabilities, etc. One motivation for studying that is trying to understand a puzzle about RHIC physics, which is how come that these colliding ions reach thermal equilibrium so fast? That's a bit of a puzzle. One caveat about that, however, is that that initial evolution might not be strongly coupled enough for this description to apply. Nevertheless, I think understanding far from equilibrium properties of quark gluon strongly coupled plasma is probably very interesting. The second comment is that a lot of work has been devoted to study these axes down here, basically at zero baryon density. But of course, we are very ambitious, and what we would like to understand is the whole phase diagram for QCD, meaning also this axis, the baryon density axis. And it's interesting to study that at strong coupling, and therefore to use holographic methods for that. But I should tell you about two caveats. The first one is that a lot of the models, including the ones I've been discussing, have scalar fields in them. And so turning on a chemical potential is likely to have a very different effect than it has in QCD. Namely, you're more likely to induce Bose-Einstein condensation than building up a Fermi sea. That's the first comment. However, we do have holographic models that only have quarks, namely fermions in the fundamental, and I hope we'll hear more about that from Sugimoto. And the second comment is that the phase diagram at large NC may be radically different from finite n, in particular n equals 3. For example, this phase, color flavor locking phase, depends on having NC equals and F equals 3. The superconducting phase is not the dominant phase at infinite n. It becomes so only below, I think, about n equals 1,000. Instead of that, at large n, what you have is some chiral wave, chiral density wave phase. But nevertheless, despite all these caveats, I think it's a very interesting avenue to pursue. And there's been very little work about this. And anything one can say at strong coupling, I think is going to be interesting. In relation to that, we should go away from finite density, from the condensed matter physics of QCD, and just go to condensed matter physics. And there's been a lot of, those are, condensed matter systems can be very strongly coupled, and they have fermions and other degrees of freedom, and it's interesting to see if you can study them using holographic descriptions. And there's been really interesting work very recently by these authors. And finally, I'm going to leave you again by repeating that LHC is going to run heavy ion collisions 1 month a year, and presumably, or possibly, so the temperature that's expected to reach there is twice the temperature that's reached at RHIC. And I think possibly the first interesting physics coming out from the LHC is not going to be in high energy physics, it's going to be in heavy ion collision physics. And so with that, I'll finish. Thank you.
Okay, any questions? Remarks, comments?
Clearly I wasn't provocative enough.
Okay, yeah, I knew it would be one.
Well, I mean, for this brane with the finite baryon density, if this brane is not touching the horizon, then what happened to the charges?
Thank you. The D-brane has to be touching the horizon. That's one thing I didn't have time to discuss, is when you turn on a finite density, no matter how small, that means that you are attaching some strings to the tip of the brane, going down through horizon, and then you quickly realize that there's no way to keep force balance at the tip. The string's tension always overcomes the brane tension, and they pull the brane down to the horizon. So for any value of the quark mass, no matter how large and how small the temperature, if you turn on baryon density, the brane always develops this very long and thin spike that goes down to the horizon. In other words, at finite density, there are only black hole embeddings. There are no Minkowski embeddings. Minkowski embeddings do exist if instead of working at finite density, you work at constant chemical potential. Then you can have large quark Minkowski type embeddings that have a chemical potential. And as you crank it up, you reach a value around the quark mass at which there is a phase transition then into a black hole embedding, which is, as you would expect, when the chemical potential is large enough, it induces a condensation of density. But for any finite density, there is no Minkowski embedding.
Okay, if there are no further questions, let's thank the speaker again. And then we have now our morning coffee, and we resume in half an hour at 11 o'clock.